Okay, so this will be the fifth video for Physics 114 practice final exam version B. Looking into question 21 through 25, I think I'll do for this video. In a typical golf swing, looking at 21, in a typical golf swing, the club is in contact with the ball for about 0.0010 seconds. And if the 45-gram ball acquires a speed of 67.0 meters per second, determine the magnitude of the average force exerted on the ball by the club. So this is an impulse momentum question. So impulse equals delta P, where the impulse, if looking, since it's asking about the average force, I'll describe the impulse here as F average delta T equals to M Bf minus Vi. We'll assume that the golf ball is initially at rest. So we can solve for the average force as mVf divided by the time interval. So 45 by 10 to the minus 3, make sure you convert to kilograms, times the final speed is in the correct SI units, and the time is in seconds, 0.001 seconds. The average force works out to be, let's do this calculation, so 45, 10 to the minus 3, times 67 divided by 0.001 is 3015 newtons, so to 2 sig figs is 3000 newtons. So that's choice B. That's the correct answer. Okay, I'll move into question 22. A railroad car of mass m and speed v collides and sticks to an identical railroad car that is initially at rest. You can assume that there is no net force on the two-car system, so that means that the change in momentum is 0, which means that Pi equals Pf. Consider a system of the two railroad cars. What is the ratio of the final kinetic energy to the system to the initial kinetic energy of the system? Okay, so looking at the changes in kinetic energy. So we sort maybe I'll just draw a quick sketch here. You have a railroad car and second identical railroad car, where the initial one is moving with a speed v, the other one is at speed is at rest, and afterwards they stick together, moving with some common speed, and it'll be actually half of the initial speed, but I'll show you how to get that. So the initial momentum equals the final momentum. The initial momentum is just mv, because one of them, the other car is, as I mentioned, is initially at rest. And then they stick together, and so that means they move with an m plus m times v final. That's 2m. So mv equals 2mv Vf, so we cancel out those m's, and you can see that the final velocity is equal to half of the initial velocity. So we're doing trying to calculate a ratio of the initial kinetic energy to the final kinetic energy. So I'm doing final over the initial, so kf over ki. So we're doing 1/2 the total mass of the final. You have to think they're moving together, so there's double m, and they're moving with v over 2 all to be squared. There's only one car, or railroad car, moving initially, so that's just m moving with speed v all to be squared. So we can cancel out those halves, so we can cancel out those m's. We'd end up with a v squared in terms, so maybe I'll just go ahead and just show what we end up here. We'd end up with 2v squared over 4 divided by v squared. So those v squareds will cancel, and we'll end up with 2 over 4. So the ratio is 1/2. So 0.5 is the answer to question 22. choice E as the correct answer. Okay, let's move to 23. A block of mass 6m is initially sitting on a frictionless surface at rest. The block undergoes an explosion that's entirely internal to the system. Let the positive x direction be to the right. The explosion splits the block into two pieces of mass 2m on the right, 4m on the left. The velocity of the block with mass 2m is v0 in the positive x. What's the velocity of the mass of the 2m? Okay, so again, I'll draw a picture here. And we've got initially we've got a block. Let's see, we've got a block here of mass 6m, and it undergoes an explosion. So the initial momentum of the system here is 0, and since if I think about the system of the block itself, there are external forces, but there's no impulse, so the total momentum of this sort of, even if it splits up, the momentum must be constant. So what we end up is a 2m on the right and a we got a 2m on the right and a 4m on the left. And the 2m is moving with a speed of v0 in the positive x, and this is moving with some speed v that we don't know to the left, but the total momentum must be constant. Again, so there's the impulse is 0, and there's no net force on the system of the 6m block. The force that caused the explosion is internal to the system, so it won't change. There's a conversion of sort of chemical energy in the stored sort of explosives, but that gets, in a sense, gets converted to, there's energy conversions, but there's no impulse actually on the system. So whatever momentum the 2m carries to the right, the 4m block must carry the same momentum to the left. So we're sort of setting pi equal to pf. This is equal to 0. This is equal to 4m times some v final plus 2mv, v0. So I can see that the v final will equal negative 2m v0 over 4m. Cancel out those m's. 4 was 2 and 4 twice. So we'd have negative 1/2 v0. So v0 over 2 in the negative x direction, which is choice A. So I can change this now to v0 over 2. I mean, they both have equal momentum magnitudes, but one is moving to the left, one is going to the right. Okay, let's look at question 24. Two gliders x and y of mass mx and my respectively are involved in a collision on a frictionless track. The mass of glider x is less than that of glider y. The initial speed of glider x is greater than that of glider y. After the collision, gliders x and y move in opposite directions with a final speed, same final speed. Is the magnitude of the glider x initial momentum greater than, less, or equal to glider y's initial momentum? Okay, so good challenging conceptual question for this one, and because there's lots of sort of competing quantities here, so we don't want to fall into that compensation reasoning, and that can be sort of dangerous in this particular problem. So we want to apply the rules very carefully. So we know that the important information here is the mass of glider x is less than that of y, and the gliders x and y move in opposite directions with the same final speed. So if we think about if mx is less than my, then the momentum to the left at the end is less than the momentum to the right. So the momentum of the system is to the right. So because again, so they're moving at the same final speed, mass x is less than mass y, so again, my is going to carry a greater momentum to the right, so the system's momentum is to the right, which means it has to be always to the right. It's a level frictionless track, so the momentum at the beginning of the system must be to the right. So since x only has rightward momentum and left has y has momentum to the left, the momentum of x must be larger than the initial momentum, larger than that of y, so greater than is the correct answer. Okay. So we can do our, as I sort of mentioned, the diagrams from the tutorial, and just to sort of do as a sort of a confirmation. So if we do initial and final, and we do let's do factor x, y, and the system, and we know in a sense the key information is that the masses are different. X means smaller than y, but the final speeds are the same. So if I were to pick, let's say, the leftward momentum here of, let's say, 4 units, that means that if y would have to be larger, let's say it's 6 units, so therefore the system would be 2 units to the right. This would have to be 2 units to the right. If we assume it's level frictionless track, there's no net force in the system, no impulse, no change in momentum, then we can see that y has some sort of momentum to the left, and it looks like its initial speed is larger than its final speed. So I might need to pick something like, I'm going to run out of room here, but maybe I pick 8 to the left. Therefore then, in order for the momentum of the system to be 2 to the right, the initial momentum of x must be 10. I'm not drawing these perfectly to scale, but the numbers are consistent. These are just arbitrary numbers that are consistent with the information given, but that the initial momentum, it still confirms that the initial momentum of x, px initial magnitude, is larger than the py initial. Okay, so that's 24. Keep going here to 25. Moving into work and energy. Okay, so a person pushes a 4 kilogram box 3 meters across the floor with a constant horizontal force of 82 newtons. At x equals 0 meters, the box has a speed of that, 0.5, and at x equals 3, the speed is 3. What is the change in thermal energy of the box floor system? Okay, I guess I could have added a rough floor just to indicate so that there is friction here. But you should, if you were to solve this particular problem, maybe I'll do this more of a sort of a teaching sort of example. 82 newtons times 3 meters is the amount of work done by the person, which is what, 246 joules. And the kinetic energy is 1/2 of the mass, which is 4 times the final speed squared, 3 minus 0.5 squared, which we'll find is not equal to the amount of work done. 0.5 times 4 times 9 times times a quarter minus a quarter is 17, make sure I did it right there, 17.5 joules. So a lot of the work that's done by the person doesn't really go into changing the kinetic energy of the box. It mostly goes into changing the thermal energy of the box and the floor. So if I sort of now think about the question itself, if we imagine the floor box system, and sort of maybe including the air that's close to the surface of the floor that might also heat up a little bit, we would have the work done on that system equals the change in kinetic energy of the box plus the change in the thermal energy of the floor. So the change in the thermal energy would be equal to work minus delta K. We've just solved those two values up there, so 246 minus the 17.5 joules. So sort of around the 229, I'm guessing. Yeah. 229 joules for the amount. So most of the person's 246 joules is going into change in the actual sort of temperature, that what we refer to as the thermal energy of the floor itself and the bottom of the box, and then a small bit of it goes into changing the speed of the box. So that gives us choice B is the correct answer. And as you can see, there's some distractors here. The 17.5 is there as a distractor, and the 246 is there as a distractor. Okay, but they're obviously incorrect answers. Okay, maybe I'll just do one more, since I know there's 32 questions to, and I want maybe just do one more video after this. So I'll just keep going with a couple more, or see if I can get what I can get done. A block of mass 0.6 kilograms is held against a horizontal spring with spring constant 200 newtons per meter. The hand is then released. It is known that the block has a speed of 0.5 meters per second, x equals 4. What is the speed of the block when it is at x equals 2 centimeters? So this is sort of a, again, energy conservation problem where the spring is going to give up some energy in basically relaxing from 4 centimeters from its stretched length to 2 centimeters. I should really say that 0 sort of represents the equilibrium, position of the spring. That should sort of be added. And that energy will go into, so if I pick the system of the sort of spring in the block, after release, whatever decrease in potential energy there's going to be an increase in kinetic energy. There's no work done on that system. All the external forces don't do any work. So there's a nice conversion of spring potential to kinetic energy. And there's a small nuanced thing here. You do not want to be applying 1/2 k delta L squared for the spring potential energy, because we're changing it from a stretched position to a less stretched position. So we need to apply the change in potential energy correctly as 1/2 k xf squared minus xi squared. And that's the correct definition of the change in spring potential energy. So we'd have 1/2 of k, 200. It starts out from going from 4 centimeters. That means it's stretched 4 centimeters from its equilibrium, so 0.04 squared. It goes to 0.02 squared. So this will be, actually I did initial minus final, so it's 2. It should be negative 0.04 squared. So this should be a negative value. So 0.5 times 200, 0.02 squared minus 0.04 squared. So we get a change of potential energy of negative 0.12 joules. So again, since the system, once the hand is released, there's no more energy added into the system or removed from the system of the block and the spring. So if the spring loses 0.12 joules of energy in going from 4 to 2, the block gains 0.12 joules of energy. So the delta K of the block is 0.12 joules, which is 1/2 mVf squared minus Vi squared, and it has some Vi. So we're trying to solve for the speed of the block, right, at 4. So Vf would be equal to the square root of 2 times 0.12 divided by the mass, which is 0.6, plus the Vi squared, which we know is 0.55. And that's just doing the algebraic steps in my head. First multiplying both sides by 2, dividing both sides by m, and then bringing across the Vi squared, and then taking the square root. And that should, let's see what that gives us. So that gives us 0.84 meters per second. So it should be, of course, should be larger. And that gives us choice B as the correct answer. Okay, so yeah, that's 26. So I think that's 6 questions. So I'll do the 27 then through 32 in the last video for this particular exam. I'll follow up with that next.